folks, Assalamu alaikum. I'm Mohammad Shahriar, almost second method. So this is our third video on the mathematics on machine learning. So today we'll start from singular value decomposition. So yesterday or the earlier session, what you have seen is we have talked about agent decomposition. So just to have a quick summary of the agent decomposition, we'll also check the coding exercise. Okay, so let's go there. Okay, so we are here. So the Jupyter notebook, I will again share that in the description, so you can just check that out. Okay, so first of all, you can see there is a matrix which has value 4, 2, minus 5, minus 3. Okay, great. So what we can do is, this is matrix A. Okay, so what we can do is by using this matrix, we can basically get, or basically using NumPy, okay, we can pass these vector matrix A using NumPy, pass this through the EIG function, and what we get is, we do get two things. One is lambdas, which we have written. This is not lambdas, basically this is our eigenvalue, and this is our v, which is eigenvector. These are the two we can get. Okay, this is basically this is via using NumPy's eigen function, okay, EIG. Okay, so once we get that, this is what we do get, which is 2 minus 1. These two are our eigenvalues, and if you are not aware of what eigenvalues are, what eigenvectors are, so you can check the previous video on the series. Okay, you can just check that, like how that impacts. Okay, after we multiply a matrix with a eigenvector, eigenvalues are the factors which tells us how much the eigenvector has scaled or not, or decreased. Okay, this is what we can know. So if you haven't seen that, you can just check the video on the series. Okay, let it be. So lambdas, we just called it lambdas. So this is how we showcase our eigenvalues. So 2 minus 1, no issues. Then this is our eigenvector, and what we are saying is that using this we can get our eigenvalues and eigenvector, no issues. But there is an equation which says, if we multiply here v, this v is basically our eigenvector. If we multiply this with this one, which is called uppercase lambda, which we show is just something like a, but it's not a, and we then multiply this with v inverse, then these three, if we multiply this, all of these three, we do get a. So the point is, using NumPy method, we can actually easily get v and uppercase lambda. Easily we can get that. As we do get this one, as we know a matrix, we can easily get the inverse of a matrix. Then if we do multiply them, we can again get back a. Now you can say, why are you doing all these kind of things? This will make sense. This will make sense once we go for much more stuffs. Okay, so let's go back to our slides and we'll talk about it right now. Great. So we have talked about Eisen decomposition, right? So yeah, that's it. So Eisen decomposition. But interestingly, so the decomposition of a matrix into eigenvectors and eigenvalues reveals characteristics of the matrix as a whole. And the matrix is singular if and only if any of its eigenvalues are 0. These are the rules and others I have mentioned earlier, so we will just skip that for a while. Now we can't get Eisen decomposition, or we can't do it for all kind of matrices. Okay, but there is this thing which is called singular value decomposition. Using that, we can actually decompose a matrix to eigenvalue and eigenvector. Okay, here for example, if we have m number of rows, for example 10 rows, okay, and we have 3 columns, assume that, okay, 10 into 3, okay, 10 rows 3 columns, so something like that, which is not a square matrix. Okay, it is not a square matrix, right? So using something like that, using SVD, which is singular value decomposition, you can get a U matrix, then a D, then a V transpose. So what are these? That's the question. What are these? So here, if you just look into that, first of all, this u, which is a left singular vector, which from here we will have left singular vectors. It is going to be a matrix where we will have a lots of left singular vectors, as it is in the left portion, so that's why we do call them. Then here d, this will be something like a vector. Okay, we will look into that. And this vt, this will be a matrix again, V transpose, that we are understanding that okay, V is some sort of our eigenvector, and we are just going to get VT, V transpose. Now let's look into the examples. I've created some examples, so while we look into that, it will make sense. Okay, if you just don't understand this is our X. Okay, let me just write it. Okay, assume that we have a matrix which is which has the value 4, 2, -5, -3. Okay, no issues. Now if you want to find the determinant of the matrix, okay, what's the determinant of the matrix? If we can represent a matrix using some sort of scalar value, which is determinant. Okay, so the determinant is -2. Now if you just want to remember how we can find the determinant, you can do so, or you can just ask for the from AI or check our videos, right? Maybe in our first or second video we've just already mentioned how to find determinant. Right, now we can easily find the determinant, which is -2 here. Interestingly, I have also mentioned that using eigenvalues, which is lambda, the multiplication of the eigenvalues also gave us the determinant. So here you see, using our code in the VS Code, you can easily see that this is some sort of matrix. So if we want to find its eigenvalue, we can find that, which can be something like that, 2, -1, whatever it is. So these two are both eigenvalues. Now if you multiply both of them, 2 into -1, which we get it right here, -2 is 2 into 1, right? So this process of getting determinant is one process, and the process of getting determinant using multiplying is another process. But why are we learning too much process? Because our main goal is, first of all, when I talked about the determinant, it was the normal one, like okay, this is how we can find determinant. But as we are doing lots of process in our computers, so we have to make it easier for the computer so that it can compute easily. If it is if you mention, or if you actually code or design the problems in such a manner, or design the solution in such a manner that it will take the computer lots of time, much more computation, the more computation like calculation, adding, or subtraction, etc., the more you tell the computer to do that or instruct the computer to do that, the more time it will take. So it's our responsibility to find easier ways. So this is one of the easier ways, right? Using just a matrix, you can find these eigenvectors, then you can just mention, okay, multiply them, they're gone. Because you can see it's a small matrix which has 2 rows, 1 row, 2 row, and 2 columns. But you may have a huge matrix, 100 into thousands, whatever it can be. So then it is tough to get the determinant using this method. And if you are not sure what the method is, which is we just have to multiply like 4 into -3 minus, right, like this, right, then 2 and 2, then minus, which is what we have, -12 plus 10, which is -2. This is the process. Okay, so there's a process. You can just follow the previous video to know the process. Okay, now talking about this, as I mentioned, from a particular matrix we can get both its eigenvalue and eigenvector. So this is its eigenvector, right? We can get that. We can we will have the code. You will see how we can do that. You can do these things mathematically or in your paper as well, but the process is not totally mentioned in our videos, because we are not focusing to how focusing on teaching the mathematics, rather introducing you the mathematics and making you understand, like okay, this is where it is used, that's it. Okay, because otherwise it will take a lot of time. Okay, now this is what we have got from X. Now we can also easily get the reverse of it, right? So we can get that. That's another process you can look into. So that's another thing which you can learn from YouTube videos. Okay, from YouTube videos. YouTube videos. Okay, let it be. Now let's move on to interesting parts. Now what we are looking into right now is, just a moment back we were looking into A equal U dVt, right? But other than that, we have also seen A equal V, then upper case lambda, then V inverse, right? So in our code, I did mention that you can do that, right? Then again, let's verify that. Okay, let's verify the Eisen decomposition. What is this uppercase lambda? Which is basically just if you just look into that, you can see we have 2 minus 1, right? Now it has row 1 column 2, row 1 column 2, 2 columns. Okay, but to multiply a matrix, there is something like we have rules, right? We need to make sure that the dimensions are correct. So we'll just modify this with some 0 value, so that in the diagonal we have the Eisen values, and diagonal mean this, in this portion we have Eisen values 2 minus 1, which we got here previously, right? 2 minus 1, and then we just provide here, and otherwise we just provide 0 out here. Okay, we just create a matrix. We can just create a matrix just like that. Okay, that's no problem. This is a trick, or this is something we need to do. We have got the V as well. So from X we got lambda and we got V. So using lambda we have created this uppercase lambda matrix, and using V we just have V, no problem. But we also need V inverse. We can just do that. You have to Google it, or you have to learn it how to do the inverse, but it is not needed in our mathematics. But you just, if you want to learn, you can just go for that. You will have V inverse, no problem. Now if you multiply all of this here, V uppercase lambda and this, you will get A. Okay, this is to verify. Okay, this is where we are verifying that our Eisen decomposition works. Okay, composition works, right? No issues. Now what? Then another thing, in our VS Code we have again seen earlier in the last video that a matrix can again be represented using orthogonal matrices. Here Q is an orthogonal matrix. So what is orthogonal matrix? If a matrix transpose is multiplied with that matrix and we get identity matrix, we can call that orthogonal matrix. Or you can say again, like if a matrix is multiplied with this orthogonal matrix, you can call it, transpose matrix, you can, and you get the identity matrix, you can call that particular U as orthogonal matrix, no problem with that. So there is an example, obviously there is an example, but what you can do, there are a lot of things, right? These are the principles, or these are some sort of natures we do look into, right? Okay, now for example, if we have A which has okay, let me just clear that, which is 1, right? It should be 1 here. Okay, 2 1 1 2. Okay, if this is 1, we can decompose it into this, which is Q, and this was basically, you can understand that the 3 1, this was lambda, but using that we have just formed this uppercase lambda, and this is actually the transpose of Q. Why not? You can understand. Like, let me show you. Here we have 0.70, right, and minus 0.70. So this whole row will be converted to a column. You can see this. Yeah, this is converted to a column, right? And this one will 0.70 has converted to a column. So this, you can call it transpose. So if you don't know, if you're not sure about what a transpose matrix is, you can look into that. Now if you just multiply them, you will get it. So yeah, this kind of things. Now you may ask, why are we talking about it? So what could have happened is, if there is a matrix like this one, 1 to 2, 2 1 1 2, what we could have done is you would have looked for the eigenvalue and eigenvector. Okay, eigenvalue and eigenvector value. So you would have got lambda equal 3 1 and eigenvector as this one q. So and you could have seen that okay, this is q, no issues. But there is an interesting thing, because if you use q and multiply it with qt, which is transpose of the matrix, you will get identity matrix. So it is easy for you to calculate that. That's the reason we are talking about it, because here you see a equal v uppercase lambda into v inverse, right? Inverse is something you have to know the mathematical process. But if you want to go for transpose, you don't need to go for mathematics, how it works and so on. You can just easily say convert this row to column, then done, qt is done. Then you can easily go for that. So this is an easy process, right? We're just learning much more easier process than the earlier, right? This is how we are going now. If we just go into our code, we can just look into that. Okay, so here as mentioned, a equal 4 2 minus 5 minus 3. So as mentioned, 2 minus 1 is eigenvalues. So here we have the eigenvector. So is the v inverse, which is obviously the inverse of this vector. So if you just multiply all of them, we can easily get here you see, if you multiply all of them, here this is v, this is our the multiplication of these two. Okay, lambda, which is which we are meaning this one. You can see we get converting this 2 minus 1 to something like that, which has 0 0, which we are calling lambda. So and we are multiplying it with the v inverse. So if we just multiply them, that is dot product. We have also talked about dot product, and then dot product that value with v, we get 4 2 minus 5 3, which is exactly what a was. That means it verifies. That's the thing. That's the thing. But interestingly, you have to learn this here. That is, Eisen decomposition is not possible with all matrices, and in some cases where it is possible, Eisen decomposition involves complex numbers instead of straightforward real numbers. That means here you can see we have some sort of real numbers, right? 0.70, 0.31 and so on, 2 minus 1, all are real numbers, plus minus whatever it is. But we do have something called complex numbers. So using Eisen decomposition, if you use that, sometimes you will get those complex numbers. So it is tough. But again, in machine learning, however, we can also look into this process, which is where Q is basically an orthogonal matrix. So if you just check into this example, it's exactly the same thing, but you can easily get the value, and you can easily do the process. So okay, let it be. Now let's focus on this one, which is our SVD, singular value decomposition. As mentioned, we can be decomposite. We can use the singular value decomposition to get what? U, D, and V transpose. So what is U? U is basically a orthogonal matrix which is of size m into m. Now that's an interesting thing, and its columns are left singular vectors. You will see that I have the example written already. You will learn about it. V is an orthogonal matrix which is of size n into n, and D is a diagonal. Right? Diagonal matrix which is m into n. Elements along its diagonal are the singular value of A. Singular values of A. Interesting. So singular value decomposition. So you are getting from the D is something called singular values. Now, for example, if you just look into this one, which is -1, 2, 3, -2. So in first row we have -1, 2. In second row we have 3, -2. In third row 5, 7. No problem. Okay, using SVD, which in NP, which is NumPy. In our NumPy there is something called SVD. So they have already done the process, the mathematical. You just have to call it. You can, using that, you can easily get the value of U, D, and VT. Now what is U? U is exactly m into m. Okay, I will just show you the size of the thing so you will understand. You just assume that okay, you just got U. Then VT is basically the V transpose. Okay, as mentioned, V transpose. So just we mentioned that by VT. So this is another matrix, and we have got another matrix which is D. So it's not matrix, but yeah, it's a vector. You can see just one dimensional, so you can call it a vector. Okay, now what we have to do, so using SVD we can get that, but to verify that we can again check like for example using so for the matrix A, basically using SVD we have got UDVT, no problem, we can get that. But again we want to verify that. So when we want to verify that, for particularly D, you can check into here that this small d is basically, it is a vector, it just has one row, two column, okay, right? But as a whole we have to, if we want to multiply that this particular D with other U and VT, we can't do that because of the rules and regulations we have for the matrix, the size, there are a lot of rules, right? So what we have to do is we have to make these vector or these values into a matrix where the size is equal to U and VT. So this is how, there is a technique which we do, and doing that we can create a matrix which has, you can see exactly we have the value 81669, we have this one, and we have here we have how many rows, we have 3 rows, we have how many columns, we have 2 columns, right? So in the second again, so after that you have 0 0, and here we have 0, and here we have the value here. So this is what we have to create, okay? Then we can easily multiply all of the 3. So this is for the verification process, okay? That okay, do we get the matrix we earlier had? You can see we earlier had A, and if you want to verify, you can now easily multiply, and you can say okay, yeah, we are getting the matrix. Now that's the issue, that okay, why are we learning this? You can now ask me the question. We will see this now. Let's start and let's start checking that. But prior to that, let me give you an example. Here it is, SVD. So here you see exactly the same matrix I have written or we have used in the code. I have just written here. So we have 3 rows. You can see 1 2 3, and we have 2 columns, 3 into 2, no problem. Using SVD, as mentioned here, using SVD numpy, yes, SVD method or function, whatever you call it, we can easily get this one, which is U small d, and this is another vector which is we do get here, okay, V transpose as a whole. Okay, now we do get them, no problem with that. Now what we can look into here is U is this, but let's look into the size. We have 3 rows, right, and 2 columns, 3 into 2. Using SVD, what we get is we get a 3 into 3 matrix, which is U, you can see, and this is basically, this is not a rule. The rule is basically what here, if we say this is M, this is N, M into N, so we get here is M into M, and here as we have N, so we'll have N number of values here. Again here what we'll have is N into N matrix. Okay, isn't this what we got? You see, we have 3 into 3 matrix, no problem. We have N, which is 2 values, which is small d, we got small d, right? This was U, this was our small d, and this was right, and this was our V transpose, which we got here something like if we look into here, this is 0.55, 0.89, this is this, so 2 into 2 matrix. Okay, so the benefit is the main benefit of SVD is, you can see using, this is not a square matrix, right? Square matrix is what, if we have 3 into 3 matrix, we can call it a square because both of the values are same. But if we don't have that, we cannot call it square matrix. So using SVD, we can decompose it any matrix. That's the benefit. Now in real life, actually this is the data set. In real life we will have lots of data, row and columns and so on. We'll make them a matrix, and then we will use this SVD. Now let's again also as mentioned, D, from D we can convert it to D, it's bigger D, where we will add 0 0 to make it have the equal size. Here you see we have 3 rows and 3 columns, and we have here we have 2 rows and 2 columns. Here we have 3 rows and 3 columns. Now you may say as, okay, they are not all equal. Oh, sorry, my bad. 3 rows and it should 2 columns, right? Sorry, my bad. 3 rows into 2 columns. It should not be equal, but the thing is, then we do multiply these two. Okay, so after we multiply them, what do we get? We get another matrix, then we multiply with this u. Okay, great, no problem with that. Now, or let me just verify. If you want to verify, let me just do it. Okay, as mentioned, I'm assuming you have seen the previous videos. To multiply these two has to be equal, so we have 2 no problem. The multiplication or the resultant matrix will have something like the resultant of these two will have the size of 3 into 2, right? Then we have 3 into 3, right? U has 3 into 3. Again, as mentioned, 3 into 3 matches. Then the resultant will have 3 into 2. And isn't this the one? A, 3 into 2. So this is what it is. So that's why we are just creating from D, we are making a bigger D. Now we have to know another concept, which is image. For image compression, we'll just check this. We have an image. You can use your own image as well. Whatever, you just need to download this notebook. I'll just show you. Like, assume that this is a matrix which is A, right? No problem. A, which is 2 into 2, no problem. So using SVD, we have U, we have D, smaller, we have smaller D, but we have then converted it to bigger D, no problem, and then we have V. Interestingly, understand what's happening. We have 1, 2, 3, 4, 4 values, and from a smaller D, we have created a bigger D. No problem, we can do that, right? Earlier I have just mentioned, and we do have, like, we do get in general VT, right? Using decomposition, but then we can do VT and we can transpose this again, so we will get V, right? So this is what our goal is. Okay, this is what our goal is. So what we can do here is whatever it is, if we want to go for V, we can do that, right? There are a lot of things. So my goal is not like the goal why I'm showing this mathematics is to let you know about the left singular vectors. So what happens is, we have 4 values, but there are columns, right? This whole column is one singular vector. This whole column is one singular vector. Okay, not this. This whole column is a singular vector. This whole column is a singular vector. Okay, and this, as it is in the right side, this V, we call it right singular vector. As these are in the left side, you can see in the left side, because it's, if it is right, if it is left, obviously, right? So we call it left singular vectors, and that's what we are going to look into right now before we talk about these things. Okay, let's go for that. Okay, let's look for this. Okay, assume that there was a link given by the obviously the author, but I have just removed and I have just added a photo. And how I did it is I've just added the photo here. Okay, no problem, we can just do that here. Okay, I've just added a photo, and what we can look into from here is, okay, okay, so yeah, I've just plotted this image. You can see in x-axis we have 0 to 3000. In y-axis we have almost 4000, right? 0 to 4000, so it's in the minus y, you can call it. Okay, so I've just plotted the image, no problem. Now, interestingly, as I mentioned, for the classification or for this image and others, we have just made it grayscaled. Grayscale is what? So grayscale means that we will just remove the colors, RGB. There are 3 dimensions more, so we'll talk about it in our machine learning videos, but we've just removed this one, right? Okay, so okay, now that's what we can do. So all of the codes are there. You will just need to change the image, and that's it. That will work. Okay, and you just need to, we have to provide the image and change this name. Okay, that will work. Then what we are doing is making it grayscale. The grayscale, now once we learn CNN and others, you will know like what is the dimension of the image data set, whatever it is, and then why we went for grayscale. Okay, So for now, just assume that making it grayscale make it easier for us to compute and others. Okay, let it be. So then what we can do here is we can convert these the values of this image, because every single pixel has some sort of value, to a numpy. We can do that. Okay, so and we have saved it to img mat. Okay, image matrix. Okay, no problem. Then using SVD, that's the interesting point. Using SVD, we can get three values: u, sigma, which is basically the what we can call it is our lambda, okay, and the v. We can get that, no problem with that. Okay, as a whole we can get that. Then here you can see we have our u, that is u matrix, and we have our sigma, which is the lambda as a whole. We can call it whatever you want, and this is the v. Now, why have we created this one? That's an interesting point. Just look into here. You see there are lots of values, right? But let's focus on the first ones: minus 1, minus 1.86, minus 1.8649, minus 1.86, whatever it is. Okay, let's go here. And here you can see minus 0.0186, minus whatever it is. These are exactly the same balloon. I can call it y. How? Because you see e to the power minus 2, that means 10 to the power minus 2. Okay, actually this is exactly the value here. So what it is basically, okay, let me clarify what we are looking for. We're looking for is, as I mentioned, this is a matrix, right? And I'm trying to create a vector having all of the values here in the first column. Okay, so here, so all of the columns of the first or all of the values of the first column, using from the u, we can create a matrix which we can call a singular vector. Okay, a singular left singular vector. Okay, great, we can create that from the diagonal again, from the diagonal for what, from the sigma, which we have here. You can see 1, 2, 3 and lots of values, 4.93 into 10 to the power 5. So using that we can get the first value, and which is this one, exactly this one, no problem. And again for the last matrix which we had here in the right part here, so from here we will also take the first column values, all values from the first column, and we will call it right singular vector, no problem with that. Okay, so using that you got it here. Now you might be confused, like, okay, why is this something like a row, and why is this something like a row or some sort of vector? Why is this something like a column? Because we, again, I mentioned about transpose matrix, right? And this is not like that, it's the v. Okay, no problem, just focus on that. Like, we are just taking the first column, just first column value, because for v, if you just look into here, v, we can verify here 0.10164, right? Sorry, yeah, 0.0164. Okay, this is exactly the first column. So from here we have to taken the first column. From v we have taken the first column, and from the sigma, whatever you call it, we have taken the first value. Okay, and if we multiply all of them, we can get something like that. So what's the goal? The goal is, there is a theory that's mentioned here. You can see, as eigenvalues are arranged in descending order in diagonal, so 2 are singular values. By convention, arranged in descending order in D, that's the first singular vector of u, and the first singular vector of v may represent the most prominent feature of the image. Which means, using this left singular vector and using the right singular vector, if we multiply them with some sort of diagonal, we can actually create the image again. So earlier here we have learned that you can multiply them and you can get the A. Right now we know we have an A. From here we have got UD and VT, and UD and V, whatever you call it. We have got that. And now using some technique, like we are just taking only this row, this value, and only this. We're just multiplying them, and we've got what? We've got something like that. It is not the image of the cat, right? Okay. So now what we can do is, we can increase the number of vectors. Earlier we had one, right? Only one vector, only one column we took. Right now we can take much more. See, if we take 2 here, for example, if you know Python, you will learn about it, 2, 4, something. So first of all, if we take two vectors from u, two vectors from v, and two values from sigma, then this image looks like that. If we take much more from 2, then we take 4, then we take 18, and so on, you'll see. If we take 4 vectors, okay, just assuming if we take 4 vector 1 2 3 4, we have all of those, but we are just taking 4, and we are just taking 4 diagonal values from lambda or whatever you call it, and then from v u, and we are just taking 4. Okay, if we just take 4, we are getting this. And if we increase it and much more and then thing like that, you can see when we have 64 singular vectors, if you take 64 singular vectors, you will generate the almost the same image we had. Now why have we gone for that? The problem is, you can see image matrix. The shape of this image matrix was 4032 rows, 3024 columns we had. Okay, so actually the actual A had something like, we have so many things like 4032 rows and 3000 something columns we had. Okay, that's a huge, there are lots of point in computer. If we give it to computer, if you see the representation, it is like so many pixels we have to multiply, or so many things we have to work on. Okay, now but using the singular value decomposition, what happened was, you can see we have taken just 64 singular values, singular vectors. We have taken 64 vectors. We have used 64 diagonals, and we have 64 right singular vectors. Using that, we have got something data points, which is this much. So if you compare that, now you can see we just have only like this. We have used this much data points rather than this. So it is only 3.77% of this one. That means for 451,648 is actually 3.75% of the percent of this value. That means we have reduced like almost 96.3% of the pixels. That means we have done this calculation much more easily using SVD. We have used some sort of singular value vectors or a singular value technique. We have just calculated that. We have just like multiplied them, and we have easily generated the image. That means otherwise, if we would not have used this one, otherwise we would have to use that obviously this much data points. But right now we just use this much data points, which is almost very less than this value is very less than this value. Okay, so that is the beauty of using SVD. Okay, then we will learn about the Moore-Penrose pseudo inverse. Okay, so now let's start the Moore-Penrose pseudo inverse. But prior to that, let's just recap. So what we had earlier was you can see here. So here we have two axes, right? For example, it can be x and it can be y, and we have 1 2 3 three lines, 1 2 3, right? Here you see. Basically I mentioned what happens is the number of lines we have are basically the rows in a matrix. Okay, number of rows, for example here maybe 1 2 3 4 4, and we might have 2 columns, so it's 2. So what it means is we have these two columns do refer to the axis. Okay, and 4 means there are 4 lines. Okay, so this is what it is. Now what happens is, you can see there are like this one point here, one common point here, and one common point here. So there are almost 3 points, which is over deterministic or over determined. We want to look for one. Like our goal is to like go for maybe the points to go for just one central point, like one common point. We just want to look for one, but it's not here, right? Now the thing is, there is another thing which is called underdetermination, which is what you can see there are 2 axes, that means x and y. So we can call there are 2 columns, but here we have just one line. That means we might have this kind of thing, maybe 1 row, right? 7 2 something like that, and which is 1 row 2 column, right? 1 row 2 column, right? So this may indicate to this line. Okay, In general, this can be something. Now I'm just using some sort of demo, but this is what it is. So we have here, we have row 1, column 2. Here we have row 3, column 2. Here what do we have? So we have another few scenarios out here, but this is not here we again row 2 columns, and we have 2 rows. Here we have same thing. This is exactly the same thing, right? So in all of these scenarios, what happens is we are unable to like get the exact the solution we do have. No, again the thing is, we also have like, this is what you have to think, like a matrix which is basically square basically follows particular rules here, right? Again, a matrix which is not square, singular, all columns are linearly independent, and we cannot actually get solution for all of these scenarios. Okay, this is the main goal. For all of these scenarios, 4 scenarios, we can't get solutions. But this is what was mentioned earlier. That was something what we learned when we were trying to look for the weight equal to, maybe I'm not sure, x inverse y or something like that, right? Something we have learned earlier using the inverse matrix. So this was the scenario, but there is an interesting factor, that is when we don't have a square. Like this scenario is particularly like a matrix is square when number of rows is number of columns, but like you see avoids over determination and so on, it has to be avoided, there are a lot of rules. So alongside that, these are the scenarios when we can't get the solution, but note that solving equation may still be possible by other means if matrix can't be inverted. So especially again, these are the scenario, again we can't get the inversion matrix as well. So what's the relation between inversion matrix and the solution? You see W equal x inverse y. Here W is a matrix, x inverse 1, this is again another matrix, y was another matrix. Obviously to get a solution for W, we need the inversion and then multiply it with y, right? Isn't it? We have to look for that, these two, x inverse and y. If a matrix can't be inverted, then surely we can't get solutions. But there is an interesting factor, that is there is something called pseudo inverse. That means pseudo means not really but kind of inverse. Okay, so here you can see that other matrix which we meant is basically this one. Here you can see for some matrix A, its pseudo inverse is A is something like plus, right? So it is its pseudo inverse, so we can call it a pseudo inverse. Okay, so how do we get it? To get it, you have to first of all get V, and then D is pseudo inverse, and then use transpose matrix. Now where U, D and V are SVD of A. Interesting, isn't it? Because using A and like if we have a matrix and we want to use SVD, we will get easily, what will we get? U lambda or something like that, and what? UV and U lambda and V, right? We will get that like that. We will get all of these values, and then when we are verifying, we'll use the transpose as well. No problem, we'll get them. Now the thing is, you can easily see this lambda, using this lambda when we are multiplying again or verifying, we are just making it something we are using 0, 0 and others to make it D, right? Isn't it? Then this D can be converted and be created something like D, something like that, which is called pseudo inverse of D. We can create that, and we have got V, we have U, and we can just use the transpose of U. We have got U, right? Where, yeah, here we have lambda. From here we have created this, and from B we have already V. So using that, we can easily get a pseudo inverse. Now you may ask, why do we need this? Interesting question, but this interesting question will again be answered here. Here we can easily look into that, but prior to that, let's just focus on some sort of like how can we generate them, right? Okay. If we go here in our example, you see the Moore-Penrose pseudo inverse. So assume that we have a matrix which is A, no problem. Then this A matrix is minus 1 2 3 minus 2 5 7, no problem with that, that's good. Then we can use SVD to get U, D and VT, which I mentioned here as well. So we can get SV, U, lambda and VT, right? As I've removed, because we have to then transpose it again to get V, okay? So I'm mentioning it again, okay? We have a matrix. We can use SVD to get what? U, lambda, VT. Okay, no problem. Great. Then what? You see, then we have U, we have VT. That means V transpose, okay? Transpose and this D. Then our goal is to, as I mentioned, from D we can create D pseudo inverse. So first of all, we have to create this diagonal matrix for the size, for as I mentioned here as well, because we have to make it in the same size as, I believe, what as U, so that we can multiply with it and then multiply with V and so on, a lot of things. So we have to think, we have to check the dimension of the U. So I have already mentioned about that here. You see, from D we have created the big D, sorry, from lambda we have created big D, and from here here again, so this was created again from depending on the dimension of this. So this is something you start learning from observation. This is not fixed, okay? So don't be worried about it. So this is what it is. Okay, so we can first of all create this one, like we have adding 0 0, so to make it a matrix and something like that. Then how to create a pseudo inverse matrix? First of all, we have now a diagonal matrix. That means we have all the values in the diagonal and the values are from D or lambda, whatever you call it, no problem. Then each of the values should be reversed. That means 1 by the value reversed, okay? Then what? Then that value will be there. That is it, okay? Now that is how we do create our that means what I would say, reverse. Obviously we are adding the reverse, but that is not the end of it. The problem is we also have to add another more column. I will just show this thing in our example out here, no problem with that. We'll just talk about it. Okay, let me just add that so that it's easy for you. Okay, let me just add that. Okay, A, what's the value of A? A is minus 1 2 3 minus 2, minus 1 2 3 minus 2. Okay, okay, let me just do one thing, that is I can just take this one. Okay, so this was our example. So minus 1 2 3 minus 2 5 7. So as mentioned, using NumPy's SVD, there is what you can do. You will get U, you will get lambda, you will get V transpose. Okay, great. So we have U. So I am not adding the value of U. We have lambda, some sort of values in lambda, and we have some sort of values in V. So let me check the value for lambda, which is D here, which is 8.6 and 4.10. Okay, for this we have 8.6 and 4.10. Great, no problem. We have 3. Now as mentioned, U has lots of rows and lots of columns. Okay, lots of rows and lots of columns. So but this lambda just has it's a vector, something like that. We have 1 row 2 columns. So let me check here. Can we do this? Can we do this? Okay, I will just add another code which should be U dot ship. Okay, run all. Let's do that. Okay, it's running. We're just running all of the codes, and I'm just trying to check the shape of these array. Although it's not yet done. It's taking some time because obviously you can see still it's taking some time. So assume how much time it will take for how much time it will take in the real world competition, right? Isn't it? Okay, great. It's taking some time, so we're just waiting for it. Okay, we can see that already. Great. Let me just add run, and for D I'll just add another, which is D dot shape. Sorry, let's add this one. Okay, so we have just two values here, and that's how it shows. And we have just two, and VT is 2 into 2. You can see VT is 2 into 2, 2 rows, 2 columns. And our U, this shape is basically, it shows us how many rows and columns we do have. So here we can see we have 3 rows and 3 columns. So you can see 1, 2, 3, 3 rows, 3 columns, right? Great. So our goal right now is first of all, using the D or lambda, whatever you go for that, we just first of all generate some sort of, create a diagonal matrix first of all, because we have two values. So we just create or add them in 4 point or something. We just add them, okay, and we create a diagonal matrix, okay, something like that. And then we will look for like, okay, where to multiply and others. But here interestingly, as we are looking for pseudo lambda, whatever you call it, here D, you can call it D, from lambda to D. So let me just make it easy for you. So there is something like that, D. So we have something 8.6 and 4.1000. This is our D. Now the goal is to go for the pseudo inverse. So pseudo inverse is basically we'll inverse them in the point. So 8.6 1 by 8.6 0 0 1 by 4.10. So we will have some sort of value, which are, I believe, yeah, 0.115, 0.243, 0.115, 0.24300. But it is of shape 2 row 2 column. Okay, right. Now our goal is, again, let me just verify again, that is, we want to multiply these 3, right? We want to multiply these 3 to get what? As mentioned in our slide as well, you can see, sorry, my bad, here, as mentioned, you can see A pseudo inverse equal V D pseudo inverse U transpose. So this is what we are trying to look into. This is what we are trying to find. So we want to get A pseudo inverse, but prior to that we have to multiply with what? Again, V, I believe it should be V, and then D pseudo inverse, and U transpose, right? Transpose. So as mentioned, U has the shape of what? So what we can do, it totally depends on the calculation. Let's see how they have calculated. So D plus plus, if so here for the D plus, so we want to calculate D plus with UT obviously, and then with this one. Okay, no problem. So the shape of this one is 2 into 2, no problem. But you see U we have, if you just look into here, U, where is that? U, it is 3 into 3. So if we even get the transpose, it will again be 3 into 3, right? Because this whole row will become column and so on. I believe you know U transpose, what should be U transpose, I believe you know that. So it will be 3 into 3, no problem in that, it will be same. So its size is 3 into 3, no problem. What's the size of D plus right now? 2 into 2. What's the size of V? Because we have V transpose, to be honest, right now. We have V transpose, to be honest, right? We have V transpose. Then U, as you know, as I mentioned just a moment back, that is, if you have V transpose, if you transpose it again, we get V, right? So we'll just do the same thing. We'll do the same thing, but the dimensions are going to be same, right? The dimensions are going to be same. The dimension is 2 into 2. Okay, just 2 into 2. So its dimension is 2 into 2, no problem. So our goal is first of all multiply them. So as I mentioned, the rules for multiplication is, if you have two matrix A and B, and it is maybe 3, okay, A into B, B into C. So the rule is the column of the first matrix should be same as the row of the second matrix. So you can see they are not same, right? That is one of the reasons. What we can do is we will modify this D plus in such a manner that the last value becomes 3. How can you do that? If we add another column, right? If we add another column, we have 2 rows, 3 columns, right? Isn't it? Now it is 2 rows, 3 columns, done. Then we can now, then we multiply all of both of these, and we'll have some sort of result, which a matrix which will have this dimension, 2 rows, 3 columns. Then we will again, as these two are same, then we'll multiply and we'll get a result which has 2 rows and 3 columns, right? So let's verify. First of all, if you just look into here, sorry, my bad, where am I? The inverse D plus, okay, D dot, okay, here it is. So here you see, as I mentioned, if we want to get the transpose of VT, already the transpose of V, we will get V. That is how we have already got it. So if we want to get the transpose of VT, we get the V. That's how we are multiplying this thing. So yeah, first of all, we will just add or write this down, sorry, my bad. And then our goal is to first of all multiply these two, right? D plus and then U transpose. We do that, then the resultant of that will be multiplied with this, and we end up with this. And this is actually a pseudo inverse. And now you may ask, or you may say, okay, what's the goal? What was the reason? The reason is here, okay? The reason is mentioned here. That is the reason. A pseudo inverse is a mega useful because non-square matrices are common in ML. Obviously, we can't guarantee there will be like square enough rows, same rows and same columns. We cannot do that. So in our example of the house, right, you see I mentioned the house prices are y1 to yn, and the column and in the columns we have features and there is some constant. So the constant is we do take the common and we have some sort of constant here, and we have the features here, and then using that we are calling it y, we are calling this at x, and we are calling this at w. Then we are again saying that we're saying that what we're saying y, sorry, x inverse w equal x inverse y, right? Didn't we? So here you can see. So this was an example provided earlier in our last video. So I believe you have seen that, and this is how we already have x. So we will get x inverse and we have y, and we will get the value for w. That's it. So once we get that, this is just for a small example, and you see, you can easily see it's a square matrix, isn't it? Because we have 2 rows, 2 columns, not like that, but yeah, we have 2 rows for x, right? And this is for y. So as a whole, the whole thing is a if we just sum up, or if we just add the whole thing, we'll have 4 minus 5, 2 minus 3, 4 minus 7. So we have 2 rows, 3 columns, but it's not a square. But yeah, just this part is square. Okay, so it's again not a square. In general, this is how things are represented. If you're learning the calculation in matrix, you will again see that we present the values with the matrix as well. So it's again not a suitable thing for us, right? But it's a small stuff, so we can just easily calculate that. But in real life, we have huge billions of values we do have. So in that scenarios, what we do is we basically use this a pseudo inverse. So using that, how can we solve the problems? Let's just go here, sorry, here. Okay, would be unusual to have exactly as many cases like n as features. So that's what we are saying, like a square, if you just want to have a square matrix, it might be unusual. It is not guaranteed like you will have exactly same number of columns and same number of features. So using x pseudo inverse, you can then solve this problem when you don't have exactly the same number of rows and some number of columns. Then w will be x pseudo inverse y. Isn't it awesome? Isn't it awesome? Because now you see, rather than x inverse, you can easily go for x pseudo inverse, and that is the solution for your problem. So X inverse was done when we had a square matrix first of all, then there was no singular matrix. Okay, so when we can call it a singular matrix, so whatever it is, that is maybe if we have what we have 3 4 and then we have 9 12. So if we have a matrix like that, you can call it a singular. So if we have that, we cannot go for that, because you see this is actually the multiplication. 9 is actually the multiplication of 3, 12 is actually multiplication of obviously 9 is 3 into 3, 12 is 4 into 3, so we have 3 in common. That means it is actually 3 into 4 as a whole. So it is same, so you cannot get a solution for this, or you cannot get inverse from here. So in this scenario you will fail to get a solution like W equal X inverse Y, because you can't get a inverse, but if you can get surely this one, right? So these other scenarios also, the scenarios or overdetermined scenario or underdetermined scenario, you can get solution for those scenarios as well. That is exactly the thing I mentioned earlier, that in these 4 scenarios we can't get solutions, we can't get a reverse matrix. Okay, but using pseudo inverse we can get that, and that's the beauty of the calculation. Interestingly, we did a lot of things, right? But in NumPy we have something called P inverse, pseudo inverse. So if you just use np.linl.p inverse of a matrix, you will just easily get the pseudo inverse. That means it's easy, so you don't need the math now, but you understood the mathematics, right? To know this mathematics you had to learn about obviously a lot of things, right? For the pseudo inverse we had to learn for eigenvalues, eigenvectors, and then a lot of things. So yeah, that's the thing, that's the user case you can right now know. Now interestingly, for a real world problem, let's just analyze a real world problem. So assume that the X is a can be called as a row matrix, where the doses of drug for treating a disease is mentioned. And talking about the Y, again the patient's forgetfulness score is mentioned. That means there is a relation between the dose and patient's forgetfulness score. Okay, our goal is, in real life what happens, especially talking about this one as well, right? The house price, right? Our goal was to know that the features, first of all, to know the features like the distance from the house, distance from the school, road, and so on. Depending on that we decided like this is a price. Just like that we have this solution, that is a problem, sorry. There are lots of doses, like if we have 0 dose, the client does forget a lot of stuff. So if you don't provide the client or the patient a dose for this disease, there is a score for the forgetfulness which is 1.86. There is high chance. Then if you provide 1 dose, the chance decreases. That means the client starts remembering things, and far better than previous scenario. Then again, when you provide 7 doses, it is minus 1.37. That means it is far better right now. Okay, so if we just plot these details in X and Y, you can easily see in X-axis, if we plot the number of doses for the clients, and in Y-axis if the forgetfulness score, okay, you will have these points. Okay, so if you want to understand, because in 0, you can see from here, you can easily understand. In 0, in X 0, Y was 1.86. so here 0, Y was something like here 1.86. okay, so this is how we plot these points. Now our goal is to find a line between here. Now why we want to find a line between here? Let me just clarify. The goal for linear or regression models are, for example, if you have this and we have lots of points, for example, we have lots of points, and these points do mean like, okay, for a particular X, for a particular X and Y, we have this point, right, for sure. So what we want to do is, this is the real life data. Okay, now our goal is to find a line which has the least, like from here it's a best fitted line, you can call it. That means a line from here and which will have some sort of constant values when we are creating that. And using this line, if now someone comes up and says, okay, maybe this was for 2 doses, 1.1 was forgetfulness, for example. Now if I say I want to give a client 3 doses, what will be the forgetfulness score? I will just easily get it from here, from this line. You can see I can now say 1.3, just for an example. This is why we get this line. So from this data, we will basically, our focus is to get this line. So we will get this line. You can see this is the line, and that is it. But how we got the line, I will just explain. Let's just explain this thing. First of all, we created some a row matrix which has all ones. Okay, all the values as 1. This is something ones. There is a function called ones which you can use to have all the values. How many values? 8 ones. Okay, no problem. Now why 8? Because assume we have 8 values, right, from 0 to 7. Okay, no problem. Now you can see we have added this matrix with this 0 to 7. There is something called 0 to 7. Okay, where did we add this? Interestingly, why have we done that? Interestingly, if we just look into here from this one, isn't it same? Because you see this Y has all of the house prices, and we had something like 111, and then this the features. Okay, in our example we just have the forgetfulness score here. Let me just write it here again. I believe you can refer to that right now. We have the forgetfulness score from Y0, sorry, use the black one. Okay, Y0, Y1, Y2 to Y7. Okay, this is our forgetfulness score, and we are just adding 8 ones. Okay, and then the features. Okay, these features are the X0, X1, X2 to X7. Okay, isn't it? So what's the goal? That's the interesting point, right? What's the goal? Do you know Y equal mx plus c? I believe we know. You all know. So you see, c has no variables with it. So if we just say c and m, okay, this can be, if you're assuming that this is this is w, and this is our x, and this is y. Assume that. Okay, assume that. If we assume that, we also know w equal x pseudo inverse y. Now you can say, why did you call it pseudo inverse? Why we had to go for pseudo inverse rather than x inverse y? Because you can easily see, if we just add this thing and create a big matrix, you can see we have y0 to y7, which and then 1 to 1, and x0 to x7. So which we have is 8 rows and 3 columns, right? Is it a square? No. Is it a square? No. And no, but it is not used in calculation, right? Then why does it matter? Okay, it's used in calculation, so it doesn't matter. Sure, your point is valid. So the real thing we have to look for is this one, actually this one, right? If we just look for the x, what we have, x has 1 1 1 1 1, x0 to x7. How many rows we have? 8 rows and 2 columns. Is it a square? Isn't it our target? Our target is to go get x inverse, and then we will add it with multiply it with y, then we'll get w. Isn't this our goal? And this is w, the whole matrix. But we cannot get a inverse of a matrix if it is not square. Then that is why we will try to get x pseudo inverse. So, and it is easy for us to get pseudo inverse, isn't it? Using numpy, we can just use p inverse, right? We can easily, now the problem is solved actually, right? Problem solved. The problem is solved how? We can use just p inv, and for this x basically, sorry, in x, and we will get this one, and then we'll just multiply it with y. That's it. And in our scenario, y is basically the forgetfulness score, and this is basically 1 1 1 1 and something, and x is basically the dose 0 to 7, and then using that we will get this w, right? Let me just go here. So here we have this, which is x, you can see, and you can see y. What is y? Y is here our this one, the value already in some sort of row matrix. No problem with that. We can just multiply that with our pre-inverse x. That means this is our x pseudo inverse. We can easily get pseudo inverse using this p inverse, and then multiply with it, and then that is w, right? That is w. That means you can see w here is minus, we got it, c is minus 1.76, and m is what? M is minus 469 or minus 47. Sorry, this is not minus 0.47. Okay, great. Now we are saying that, as we know that the first value is c or whatever. In our code we have just used b. You can just use c as well, no problem, and the rest part has been used as m, no problem with that. So if you use that and create a function, you can easily see from here y something like that. You can see from here mx plus c, that means c instead of c we have used b, no problem with that. You can just change it from b to c, and you have to change here as well. Then if you just do that, we will get this thing. This is the line. Now if someone comes up and says, hey, I want to use give 4.5 doses, right? Then from there, using this line, we can easily get how much the forgetfulness score is going to be. Great, interesting, right? Now let's talk about trace operator. So trace operator is here. I've just already mentioned in our slide. Sorry. Yeah, let's look for that. Assume this is a matrix which is 3 4 0 minus 5. So what is trace? Trace is basically the whatever we have here. 3 minus, so we have, it's diagonal, right? So if we just add this 2, 3 minus 5, which is minus 2, this is our trace of a. Okay, that's it. Now this is called like the summation of the diagonal values. Now the question is, why is it important? Because assume or remember, we have something called norm, right? For L2, we had to just square every value we have in a matrix, 3 square, 4 square, 0 square, 5 square, and we had to then root that, and we would get this kind of value. We can easily get that one using trace. Instead of square and something, if you use trace of the multiplication of the matrix and its transpose, you will get exactly the same. For example, here is the one, we got 7.07. Again, if we do the transpose, if we multiply them, if we get their transpose, you see this is the multiplication result, 9 12 12 41. This we have to just add them up, and that is the trace, which is 50, and then we have to root them, and we will get 7.07. Easy. Now again you may ask, hey, again why? We already knew norm. You see, in norm what we had to do, we had to square. What do you mean by square? Math in computer generally does only plus and minus. Whatever you give it, it just does plus and minus. 3 square means 3 plus what? Plus 3 plus 3. 3 3 3. So 3 square is 9, right? So it had to go for 3 plus 3 plus 3 times. So interesting, right? Again, going for others, 4 square what? 4 4 4 4 4 4 times, right? Isn't it? So it has to go actually add or sum these numbers 4 times. So it will take time. Rather than that, if you just use the taking trace, what it will do, it will just multiply and then sum up only these two number. Won't it take less time? Yes, that's it. That's why we're learning this. Now let's look for the final one, which is very much interesting. I will not be actually showing the maths behind PCA. PCA has been, even when I'm working with the quantum computing, I do use PCA, okay, principal component analysis. Even if you're using PyTorch and others, you will see there are lots of libraries which, if you just use, they will do this kind of stuff, PCAs. Okay, so in unsupervised learning, which enables identification of structure in unlabeled data when the label data is not labeled. Okay, so you may ask, what is this kind of thing? So we'll learn about this supervised model, unsupervised, and so on. So like Eisen decomposition and SVD, we have learned Eisen decomposition at the start. We have again learned SVD, which basically enables lossy compression to minimize both loss of precision data footprint. First, principal component contains most variance data structure, and second PC contains next most, and so on. This is interesting. This point is interesting. We'll see. Just within a moment, we will see. So it involves, this PC involves norms, orthogonal, identity matrix, trace operator, and others. So let's just verify. Let's just see from the example. Okay, there is a block. So if you just look into here, you will understand. But yeah, for me, I believe that was better. So if you see, we have some numbers. These are the process. You see, we will first take the mean of the values here. Then we will take what? Eisen values and Eisen vectors. I believe you have all learned about it by now. Then a lot of things happen. A significant Eisen vector and vectors, sum of Eisen values, and this kind of process, and so on. And then we end up with this last matrix. Okay, so there's a lot of process. I'm not going to get into the thing. This is totally an assignment for you to learn the mathematics. Okay, the PCA, because whatever is required for PCA is totally covered in our 3 videos. Okay, has been covered. So let's go for the PCA. So what do we get and what's the real case? Let me just give you an example. Assume that there is a matrix. There is a matrix. Okay, what kind of matrix? In real life, right now you will just understand how real life data works. Okay, assume that we have 150 data. That means from 1 to 150. No problem. Great, no problem. We have 150 for 150 flowers. From 150 flowers, we have some sort of features that has been mentioned here. 4 features, and then there is another thing that's called, which is basically called label. That means for 150 50 flowers, sepal length, you can see what's sepal. So what's the length of the sepal? What's the length here? You just look for the length, right? This is the length, this is the width, right? So for a particular flower, maybe for flower 1, the sepal length was this. The length was 5.1, and its sepal width was 3.5. Its petal length was 1.4. Its petal width was 0.2. Great. 1, 2, 3, 4. Great. Then, and we know this flower is called setosa. We are calling this is setosa. No problem. Then this same thing is repeated for remaining 149 flowers. We will just do that. No problem. We'll do that. Now, interestingly, you have to understand what's happening. Interestingly, this exactly the same thing. Let me just take this and take it here. Okay, believe that has been copied. We'll just remove that. Okay, let me just show you how real world data works. Okay, so here you can see we have 1 to 50 or something, so we can create a matrix, right, which is 1 to 3 to something 150, and there are features that is calling for, and there is some sort of label which is Setosa, versicolor, and Virginia. Okay, this thing. Now let's just again look into here. So we are using this IDs dataset, which actually has the same thing. Okay, if we just look into here, okay, this is the one, principal component analysis on IDs dataset, or you can just look for IDs dataset from scikit-learn. So same thing, the same thing has been already done, so you can just verify that. So the dataset can be loaded. The dataset is not exactly shown out here, like you can see how's the dataset, but this is how the dataset has been. Okay, so you can just use that, load that, and you can just use the SVD out here. Okay, these are how things. Okay, so yeah, this is how we can just load the data. So from here, if we just want to check the shape as well, I believe, can't we check that here? Let me just run all of the stuff. So okay, so what will happen, we'll just look into that, what happens or how to work with it. So yeah, it's happening. Okay, so once we load that from scikit-learn, you can just use that. Okay, from scikit-learn, sklearn, we'll see how to code them, import datasets, then id equal dataset.load id. So we have to do that to get the matrix, dataset matrix. Okay, so this is the dataset, and this is the dataset matrix. Okay, this is the dataset matrix we have just loaded, but this we don't have these things. Keep it in mind, we don't have this thing. We just have, just let me just make sure what you are understanding. We just have this portion. Okay, and that is I believe 1 2 3 4, right, 150. Okay, so sorry, we have this portion, right? We have 150 rows, and we have 4 features. This is what we have, 150 into 4. This is what we get using the shape. So you can see 150 into 4. Now interestingly, we were supposed to have like what, 1 2 3 150, or this. Where is this? Where has this gone? To be honest, can you tell me if this has any value to this kind of thing? Basically each row or each feature, basically if particular feature 5.1 3.5 1.4 0.2, it is actually showing it is actually referring to a particular flower, right? That means if we can have a value from this, it will refer to that. Okay, I will just talk about it, but just for an example, just assume that this is the X or something. We are just referring to 150 data, 150 values, and 4 features. Okay, sepal length, sepal width, petal width, and petal width, petal length, petal width. Okay, 150 and 4. Great. Now we have just tried to learn like what is the feature, what are the feature names. So you can see these are the feature names. That means these are our column names. Okay, column names. So we had this column, this column, this column, this column. We have this column name. Okay, no problem. Great. Then what? Then this is basically to look for like the first 6 row values. No problem. We're just trying to see like what are the values we have in here. So for the first 6 rows, you can see these are the values 1 2 3 4 5.1 3.5 1.4. This is exact 5.3 1.4. These are the exact values basically. Yeah, we're just trying to look for the first 6 values. No problem. Okay, great. So just to check the values, no problem. Then we have used PCA here. How to use PCA from scikit-learn.decomposition import PCA. This is how we load PCA. Okay, there is already the code uploaded or already there in scikit-learn.decomposition. We just have to mention this and it will automatically use PCA. Okay, now this interesting point comes up. It is very important, which is we have to mention how many number of components we are going to create from here. Now interestingly, understand what's happening. You see, our goal is to look for, or our goal is to represent the data in 2 points, x and y, in x and y axis. Okay, x and y axis. Understand that. Now in x axis and y axis, like for example from this data, if we can somehow manage this from this data point, if you can somehow manage two points x and y in a matrix, whatever format it is, whatever you call it, if we have something like x array or whatever x x matrix or y matrix or whatever we have, we can just plot it here. So what happens is, for example, we have 2 5, okay, or you can call it just 2 3 4 whatever, we have something, and 2 3 and 5 3 whatever, we have 2. So for 2 5, so for 2 5 this is the point, for 3 3 this is a point, right? Isn't it? So this is how we can plot it. So our goal is to take these 4 features 1 2 3 4 and convert it to, in some way convert it to 2 features, only 2, something like that, 1 and 2 in 2 features, x y, something like that. Why? Because these 2 can be, then we can just represent them in these 2 axes, and using that we will have some points, right? For 150 data we will have some points. That's it. That is our goal. So you can see, so we have converted the all of these 4 features in some way. That is the math behind PCA. That is totally your homework. You can learn that. So we can then get the PCA. So you see, after the process, we will end up with 150, 2. What does it mean? What does it mean? It means that we earlier had 150 rows and 4 features, or 150 data for 4 features. Now using PCA, somehow we have done PCA and we have 150, but we have just 150, obviously not 150 in the we have 150 numbers or whatever data, but we have just 2 rows, which is 1 and 2. Okay, so we have 1 to 150. So we have now two I believe 2 features or 2 columns we have. Just you can see 150, 2, and again you can check the first row value, first 6 row values. You can see it is just 2 values, and it's like -2 6 8 1 3 1. It is not related to this, right? Somehow there is a process which it uses to get the most values or most out of it from the matrix. So this is it, and using the values from these x we have, we can plot them. Okay, and plot the scatter. Okay, and interestingly, there is another interesting point, that is target, iris.target. Iris.target, that's interesting. That is what is here, that is not mentioned. If you just don't know, the target is this one. So there is something like as mentioned earlier, we have seen something like W or whatever. So here leaks SEV or something we have assigned for this particular setosa. We say like, okay, we'll understand setosa by 0, we'll under versicolor by maybe 1, and we'll understand Virginia by 2. This is what is done in real life machine learning. So rather than this as a alphabetical order or a name, we can have numbers out here. Interestingly, right? That is what means here. That means we'll have a matrix where we'll have 0 0 0 0 1 1 1 1 something, then 2 2 2 2 or something. Okay, that means 1 refers to a flower, 0 refers to a flower, 1 refers to what? Versicolor flower, then Virginia, 2 refers to Virginia, and 0 refers to this. So we can also, like, you can understand this by this, like if we just multiply them, or if we have this ASVE Virginia or something, we just multiply, this is exactly the same thing or whatever. So for our mathematical thing, because all of the things should be mathematics, so we have just decided to have 0 instead of setosa, sorry, setosa, and other flowers. Okay, great. Again, if we just here what mentions is we have 50 flowers, which refers to 0, which is setosa. We have 50 flowers, which is for other versicolor maybe, and this is 50 for Virginia. So this is what it is meaning here. We'll learn about it gradually, but this is what it's meaning. That means we have 150, right? 50 for this, 50 for this, and 50 for this. If you check this data set image from here as well, you will easily understand this here. From 1 to, you can see Sitosa, right? From 1 to 50 or 49. From 50 to 100 so no 99. From 50 to 99 we have versicolor. From 100 to 150 we have Virginia. This is what it is, right? So we have 150 colors. So this is how it is. So that is what exactly mentioned out here. Okay, so now if we plot them, you can see this color refers to a particular flower, this color refers to a particular flower, this color refers to a particular flower. Now, and this you can see C equal IDs dot target. Depending on the target, we have set the colors, and this is what it is. So you can say IDs dot target names. So this was the target names. Again, target names have been mentioned as well. So I believe I have also mentioned that we have two. So this is the target matrix. This is the target names, right? So you can now easily understand that target names. This we had the 3 values in a matrix. This can be string, no problem with that. And yeah, that's it. Then you can plot it depending on the target. Like you see C equal to IDs dot target. As you know, like you see, I believe if I'm not wrong, this should be all of these are for 0. IDs dot target, which is maybe you see target can be 0 or 1 or 2. Okay, but target names can be this. So 0 refers to, so for these all of these values, maybe these are the zeros. So they have the same color. All of these values refer to 1. So they have this greenish color, and this is yellow. So for maybe 2. So this is how what is happening is we can easily understand. Like we had 150 flowers, but we can understand. Okay, these are the data for Sitosa. These are the data for versicolor. These are the data points for this. So now what happens is, if a particular data set or particular, let me just particular flower comes up, like okay, you teacher just mentioned, hey, let's can you tell me what this flower will be? If we have a point here, you can easily say, okay, as we have lots of data here, it can be versicolor. A point here, it can be Virginia. A point here, you can call it, okay, a point, this may be a Sitosa flower, Sitosa. That's it. That is the beauty of our linear algebra. So yeah, that's it for our linear algebra. We're done. We're completely done with linear algebra. So yeah, I believe if you have any questions, you can ask in the comment sections. And thank you so much for watching this video. We had no exercise today. But feel free to check this out, and if you haven't checked the previous 2 videos, you can just check this out from the series. Thank you so much, and see you in the next video.